Welcome to this explainer. Okay, so when you look at the periodic table, it seems incredibly organized, right? It looks like a perfect, elegant map of all matter. But today, we're going to explore some massive scientific controversies and some pretty profound cosmic secrets hiding right there in plain sight. We're looking at the very first row, period 1. And as we're going to see, it is absolutely packed with anomalies.
Let's just jump right in. The periodic table is the ultimate chemical blueprint, but there is a glaring anomaly sitting right at the absolute top of it. Think about it. All the other rows have at least 8 elements, right? Some even have up to 32. But that first row, it contains exactly 2 elements. Just 2, hydrogen and helium.
So we really have to ask ourselves, why do these first 2 elements completely break all the conventional rules of chemistry? Today, we are going to treat hydrogen and helium like the ultimate chemical rebels that they are. We'll explore why they behave so weirdly and why, for literally over a century, some of the world's most brilliant chemists simply cannot agree on where to actually put them on the table.
Section 1, the quantum room. Only space for 2.
Okay, so let's start at the very foundation of quantum mechanics to figure out why this period is so exceptionally short. It all comes down to the duet rule. You can kind of think of the first electron shell, what chemists call the n=1 shell, as a tiny, super cozy little quantum room. Because of the strict mathematical constraints of quantum numbers, this space only has one single orbital, the 1s orbital. It completely lacks the space for those larger p orbitals that all the other rows have. And since an s orbital can only hold a maximum of 2 electrons, period 1 elements are totally full and completely satisfied the exact moment they get 2 electrons. That is exactly why the row just stops at 2.
Section 2, the identity crisis. Where do they belong?
Now we get to the real drama. Hydrogen is basically living a total double life. Because it's so structurally unique, it just doesn't behave like anything else. On one hand, it acts exactly like a group 1 alkali metal, like lithium or sodium. It has one outer electron, it typically loses that electron in reactions, and it can even displace metals from their salts. But, on the exact same hand, it forms a diatomic, non-metallic gas under standard conditions, which is exactly what fluorine or chlorine do over in group 17. It even forms hydrides by gaining an electron, perfectly matching halogen behavior. So, is it an alkali metal, or is it a halogen? Well, the confusion gets even deeper because hydrogen isn't highly oxidizing, it isn't highly reducing, and it totally ignores water, which is wild because those highly reactive group 1 metals, they literally explode in water. Because it matches absolutely nothing perfectly, some periodic tables just throw their hands up and literally float hydrogen. They detach it completely, leaving it floating alone at the top center of the table away from all the groups.
And guess what? Helium is suffering from a very similar identity crisis. It's almost universally placed over with the group 18 noble gases, like neon and argon, because it's an incredibly unreactive gas with a full outer shell. But if you look strictly at its structural resume, it reads entirely differently. It only has 2 outer electrons, it's an s-block element, and solid helium actually crystallizes in a hexagonal close-packed structure. That makes it look exactly like beryllium or magnesium, the group 2 alkaline earth metals.
But here's the catch. Just floating these elements away from the table is highly controversial. Chemist Eric Scarry strongly criticizes this whole floating idea. He reminds us that even the misfits absolutely must obey the laws of chemistry. To exclude hydrogen or helium from a group is to basically suggest they exist outside the periodic law itself, and that's the very foundation of chemical science. We have to find a place for them.
Section 3, hydrogen, the cosmic anchor.
Let's zoom in on the specific resume of our first shape-shifting misfit. The numbers here are just wild. Hydrogen is the oldest element in the universe, and it makes up a staggering 75% of all elemental mass. Everything else, the entire rest of the periodic table combined, is crammed into that tiny remaining 25% sliver. It acts as the plasma anchor for stars in the main sequence. Essentially, our entire universe is, fundamentally, a hydrogen universe.
But ironically, down here on Earth, elemental hydrogen is relatively rare. We can't just mine it out of the thin air. It's mostly extracted industrially from hydrocarbons like methane to fuel massive human industries. We use it for fossil fuel upgrading, like hydrocracking, and for immense ammonia production to create fertilizers for agriculture. It's also absolutely vital in metallurgy, where it can actually cause metals to become brittle, which is a major engineering challenge. Oh, and it's basically the absolute foundation of acid-base chemistry in all our laboratories.
And if we zoom all the way in to the microscopic level, hydrogen has another massive superpower. Its most common naturally occurring isotope is protium.
That's just one single proton and 0 neutrons. Why does this matter to us? Because the protium atom is literally the only neutral atom in existence where the famous Schrödinger equation can be solved analytically. By studying the energetics and the spectrum of this one incredibly simple atom, scientists literally built the absolute bedrock of quantum mechanics.
Moving on to Section 4, Helium, the sun gas.
So helium is kind of the aloof, chilled-out loner of the periodic table. And get this, it wasn't even discovered on Earth first. French astronomer Pierre Janssen first spotted helium as this mysterious, unknown yellow spectral line while he was looking at light from a solar eclipse back in 1868. We literally discovered it in space before we found it on our own planet. It wasn't until 1903 that massive crucial reserves were found hidden underground in U.S. natural gas fields, which unlocked the essential modern tech applications we rely on today.
So we have this crazy juxtaposition between cosmic helium and earthly helium. Out in the broader universe, it is absolutely everywhere, formed directly during the Big Bang and constantly being created by nuclear fusion inside stars. But Earth's supply? Completely different story. The helium we use here is actually a rare byproduct of natural radioactive alpha decay. Deep underground, radioactive elements emit alpha particles, which, if you look closely, are just helium nuclei. This radiogenic helium gets trapped down there with natural gas, where we have to carefully extract it.
And because of its rarity on Earth, we really do have to extract it carefully because we desperately need it. Helium has the absolute lowest boiling and melting points of any element. It exists only as a gas unless you put it under really extreme conditions. That makes it an absolute superpower for cryogenics. It's what cools the superconducting magnets in MRI machines. We use it in deep-sea breathing systems, as a protective gas for growing silicon wafers, and incredibly, liquid helium is used by researchers to study mind-bending quantum mechanics phenomena, like superfluidity.
Which brings us to Section 5, the misfits that built everything.
So how does this all connect to the very nature of existence? Well, the debate over these two misfits never, ever ends. Some chemists, like Henry Bent, fiercely argue that helium should officially move over to Group 2. They point to something called the first-row anomaly. This is a chemical trend stating that the first element of a group just behaves differently than the rest of the group. They argue that helium, as the first s2 element, actually has hidden properties analogous to beryllium, and its ionization trends fit much better in Group 2 than they do with the noble gases.
And that leaves us with this beautiful, incredible cosmic irony. Think about it. The two elements that give human scientists the absolute biggest categorization headaches, the elements that just stubbornly refuse to fit into the elegant columns we designed, are the exact same elements that basically built our entire universe. They are the oldest, they are the most abundant, and they are the most foundational pieces of matter in existence.
It leaves us with a really fascinating mystery to ponder as we wrap up this explainer. When the map doesn't quite match the territory, what's actually at fault? Are our rigid human rules of chemistry ultimately flawed? Or are the universe's oldest characters simply meant to break those rules? Perhaps our periodic map of matter is perfectly designed for everything that came later. Or perhaps nature just simply refuses to be put into neat little boxes. Keep that in mind the next time you look at a periodic table. Thanks for joining me on this explainer, and keep questioning the rules.